Next, we have up Jessica Fintzen speaking on representations of p-adic groups and arbitrary residue characteristic. Thank you very much.
Thank you very much for the invitation. It's a great honor and pleasure to be here and speak at the conference celebrating Jim Arthur. Thank you. All right, so I'm going to talk a bit about representations of p-adic groups. So P is a prime number. If you can't read, can't hear, or have questions, just interrupt, please. Well, if you couldn't hear that, I guess you can't interrupt that. So F is a finite extension of QP, or the Roman series over a finite field. Oops, I can't. So in other words, a non-Archimedean local field, which contains a ring of integer O and a uniformizer bar pi. Am I still on, or did this cut? Okay. And the residue field is denoted by FQ, a finite field with Q elements. And then G will be a connected reductive group over our local field F. So that's what I often call. Yep, have a look at wherever you want. I mean. Thank you. Okay, less thunderstorm. All right. I hope everyone is awake now from the sound. So G is a connected reductive group, GLN, SLN, but also G2, EH, whichever you like. And so the goal is it on now? So then I think our kind gentleman did something. Is it better now? Can people hear me on Zoom? I guess that's the real question, but they might be asleep. Is anyone paying attention on Zoom and can hear me? All right. Perfect. So what is our goal? Our goal is that we want to understand or describe very explicitly, so let me say explicitly, the category of all smooth, and let me say complex. You can also work model. For this talk, I restrict to complex representations of the p-adic group G of F, of the F point of our reductive group. And as always, smooth means that for every vector, there is an open subgroup that stabilizes it. So these are usually infinite dimensional representations, but they form a nice category. And so how can we do that? Well, we know, as we have already heard a bit from the previous talk, that there are so-called building blocks, which are the supercuspidal representations. So the supercuspidal representations are those that do not arise via proper parabolic induction, and everything else arises via parabolic induction. And so that means there are two steps. We want to understand the supercuspidal representation, the step one, and the step two to understand the rest build out of that. And so here are the two main results in vague terms. Here's vague theorem number one, and the talk will be to explain this in much more detail. And so that's due to a lot of people. And then the most recent work is my joint work with David Schween, who used to be, he's in the back, who used to be a postdoc with me and started his tenure track now at Utah. And we put this on the archive in January this year. And so the wake theorem is that we can actually construct all supercuspidal representations. So we can construct almost all. And at the end of the talk, I will make that precise. What I mean by that, almost all supercuspidal representations. And what I put our names here is because we can do this also if P is equal to 2. So what we did is to extend well-known constructions to the case P equals 2. And so the main part of the talk will be about trying to explain you why P equals 2 is so different from the rest, why this wasn't possible for the last 20 years, and what made it possible now. And so that's the first wake theorem. And yes. So the answer is that if P is large enough, we can construct everything. If P is small, we can't construct everything. I just, in wake terms, wanted to combine these two statements here. I will draw a picture at the end. And maybe I should also add all these representations are of the following form. They are all constructed as a compact induction from some subgroup K. So K is a compact mod center open subgroup of our group G. And then we take an irreducible representation rho. Rho is an irreducible smooth representation of K. So it's a finite dimensional representation. I will drop smooth. Often all my representations are smooth. And then we form the compact induction. So these are, as usual, all the functions from our group. So the vector space on which rho acts that satisfy the following two properties: f of kg is equal to rho of k f of g for all of small k inside capital K and g inside G. So K pulls out via the standard induction, and F should be the compact induction, means that F is compactly supported. So this is our infinite dimensional vector space, and usually infinite dimensional, and then an element G acts on a function via right translation. So the function gets sent to the new function that is evaluated at xg instead of at x. And so that is the idea, that we construct all these representations here via compact induction. So really what we want to do is to construct these nice compact open subgroups with nice representations rho thereof. And so let me give you a very explicit example so that you have seen a supercustal representation very explicitly, or almost explicitly. Let's take G to be SL2. Let's say F is QP for simplicity. So I have to give you a K in the row so that the compact induction is a supercuspal representation. And so I take as my K SL2 of ZP. And then I build a representation out of this by just projecting down to SL2 over the residue field. So it's FP, which is in other words the quotient of SL2 of ZP mod out by its pro-P uniproton radical. So 1 plus PZP on the diagonal and PZP off diagonal. So all the matrices congruent 1 modulo P with determinant being equal to 1. And so then I can compose this now. I have a finite group of Lie type. I can compose this with a representation, which I also call rho, which is a cuspidal irreducible representation of my finite group of Lie type. So that maps to some automorphism of its vector space. And now if I take this composition from K to this space of automorphisms of V rho and call this rho as well, so this inflation, then that is the rho up there. So then I can compactly induce from SL2 of ZP to SL2 of QP this representation rho. And maybe I should just said cuspal representation of SL2 ZP, of SL2 FP. These are just, if P is large enough, the representation of dimension P minus 1 and P minus 1 over 2. So you can actually write them down very explicitly. It's just those representations that don't have fixed vectors under the upper triangular matrices as ones on the diagonal. So it's something very explicit. And then the fact is that this compact induction is an irreducible supercuspidal representation. So that's a very concrete example, and it's not just an arbitrary example, it is an example of depth zero. And what does this mean of depth zero? Of depth zero means what is the depth? So I said we study smooth representations, which means every vector is fixed by some compact open subgroup, but you don't know what it is. And more precise, they define the filtration of the p-adic groups of their compact subgroups by smaller and smaller compact subgroups. And the depth is a measurement of how far you have to go down in the filtration until you find fixed vectors. It's either 0 or a positive number. And 0 means that I have fixed vectors under, in the case of simply connected groups, under the pro-p unipotent radical of a maximal compact subgroup. So this here is the pro-p unipotent radical. And so this works in rather full generality, at least for simply connected group. Otherwise, you have to add some more words to it. And that the depth zero representations in general, they are just the representations that are compactly induced from taking a maximal compact subgroup, quotienting out a pro-p unipotent radical, and inducing up from there. So that's in general depth zero. Another way to think about depth zero representations is that these are the representations that come from representations of finite groups, of finite groups of V type. So that's how I think of depth zero representations. They were well understood since the 90s, thanks to the work of Moy and Prasad. And so these are well understood, but now we want to understand the rest, and that's the wake theorem one that I want to say more about throughout the talk. Before I dive into that, I want to say, what can we do if we assume theorem one? How do we understand the rest? So here's the wake theorem two. By wake, I mean that I'm not very precise about the assumption. Really, what I mean, assume you have the construction of supercuspitals, then this following thing holds. And we do have them under minor tameness assumption. And I should, well, let me first write the theorem and then give credit. So, well, before I write the theorem, let me write down here. The Bernstein decomposition tells us, so Bernstein told us in the 80s what we have already seen in the previous talk, but I don't assume you remember everything. Bernstein told us that if we take the category of all the smooth representations, so that's the category of all the smooth representations of G of F, then this decomposes into a product of Bernstein blocks, which are indexed by Levy subgroup M and sigma supercuspidal representation thereof. So pairs M and sigma, where M is a Levy of a parabolic subgroup of G, and sigma is a supercuspidal representation thereof. And we take these pairs up to equivalence. We've seen in the previous talks what the equivalence is, up to conjugation, up to twist by ramified characters. And so then we have these Bernstein blocks. And so the first theorem essentially tells you that we understand all these sigmas, all the supercuspidal representation, which actually is a thing that we didn't understand for a long time. So people already knew more than 50 years ago that everything arises from parabolic induction, but they didn't know how to construct these mysterious supercuspidal representations. And so if we now take this theorem one for granted, the question is, how do we describe all the other Bernstein blocks? And here's the wake theorem. So the first part is that if we take a Bernstein block attached to some M sigma, then this is actually isomorphic to, I write down the same thing and add zeros everywhere, which is not telling you much yet until I tell you what this is and what are these. So the claim is that there exists some G0 inside G. It's a twisted Levy subgroup. It becomes a Levy after base change. And then a Levy subgroup M0 inside G0, and a supercuspidal representation sigma 0 of M0 of depth 0, such that we have such an equivalence. So let me redigest. For the principal Bernstein block, No. So you mean in the case that this is a T and this is just the character of it, this will be a T as well, and this will be a character, and the G0 will depend on what your character is. If you start with a depth 0 character, nothing interesting happens. If you take the trivial character has already depth 0. And so if you start with a depth 0 representation here, I just take G0 to be G. I mean, it's a trivial statement. So this statement, so far, what does its statement say? It says start with an arbitrary Bernstein block that we don't understand. Then it's equivalent to a depth 0 Bernstein block where the sigma 0 is of depth 0, which we don't understand yet either. So in some sense, I've told you only half of the story. The second half of the story is that we do understand this part. And that will then answer also Janis. Oh, sorry, I should have repeated. Janis asked, what happens if I take the principal block? So I take m equals t and sigma 0 to be sigma to be trivial. In that case, it's trivial on the nose. But the second statement is more interesting. The second statement says that actually we do understand all these depth 0 blocks because all of them are equivalent to modules over something that is well understood, over so-called Hacker algebra, which is a semi-direct product of an affine Hacker algebra of some affine Weil group for some Q parameters with a twisted group algebra. I don't want to go into the details of that. That can be a talk on its own. All I want you to take away is that this Hacker algebra is well understood. Let me say well understood. It's described via explicit generators and relations. And in particular, we understand the category of modules over that. So that means, yes. Yes. Oh, can I have two different G0s that satisfy this relation? Well, since a lot of, I mean, abstractly, yes. Very concretely, we usually, yeah, I mean, for GLN, for example, most of them are this, I mean, isomorphic. So yeah, I don't have a good helpful answer right now, other than you can actually construct a G0 very explicitly. It's just, well, when there's some data underlying it, and this G0 would be just the centralizer of certain nice elements in the Lie algebra that we will kind of see in the construction later on. It's an existence a priori. I'm stating it as an existent one that is actually very explicit. So we can write it down all very explicitly for you. And I didn't say it. I said that I kind of, yeah. It's a group. So I can't, I mean, it's explicitly described, but it's not easy to describe it for you on the blackboard right now. So in the case, no, so in the case that we work with, if we have the principal, so if we work with the torus and trivial character that Janis asked for, then this would be just the affine Weil group, and this would be just the stabilizer of an alcove. In general, it's a stabilizer of an alcove, but of a different affine root system that is more complicated to construct. And mu is a 2 co-cycle. So a map from that's twisting our multiplication by a complex number. And again, I'm happy to provide more details at the end. So I think the rough idea is just that I wanted to tell you that we really understand these depth 0 blocks very explicitly. I can write down all these details, not within an hour, but afterwards. And also everything reduces back to depth 0. So once you understand the depth 0 representation, you kind of understand, you can understand the rest. And that allows us to reduce a lot of problems about representation of p-adic groups to depth 0, where I've just told you depth 0 representations are like representation of finite groups of V type. So it reduces a lot of questions to questions about finite groups of Lie type where the answers are much easier to reach or sometimes already know. And I should give credit, yes. The question was, is part 2 integrally over z bar 1 over p? And so I can give you two answers. Well, the easy answer is no. The more elaborate answer is, well, the Gaussian decomposition doesn't work integrally. This isomorphism really comes from an isomorphism of Hecke algebras. That works, at least model. You still don't have the Bernstein decomposition integrally, though, but I've joint work in progress with Jean-François Dette, where we try to do the same thing integrally over exactly this ring. Or more general, I can remove the bar and take any algebra over here, but then you can't take a Bernstein block on the nose, but you have to, it corresponds to union of Bernstein blocks because the depth 0, all the depth 0 representations form one block if you work over that ring. And I was supposed to give some credit. So the structure of the depth 0 Hecke algebra was essentially already known to Morris in the 90s. Well, except he looked at connected parahorics. We need to also look at disconnected ones. And that's part of the joint work with Jeff Adler, myself, Manish Mishra, and Kazuma Ohara. Kazuma Ohara is a postdoc in Bonn right now, which we put on the archive last year. So that's doing this in general and having the reduction to depth 0. All right, so that's the big picture. So these are the two wake theorems that basically tell us essentially everything up to the small details that I said, wake and almost and things like that. And so what I want to do the rest of the talk is to tell you a bit about how to construct the supercustom representation also for p equals 2, which actually this whole construction is an input for this reduction to depth 0. Unless there are any pressing questions at the moment. All right. Does my work make the connection with local Langlands clear? Depends on what you mean by clear. So this, sorry? By this, oh, that's not getting better. So what is the relation with Langlands correspondence? So indeed, so you have for each of, well, we don't have the Langlands correspondence in general yet, but like let's assume when we have a parameter corresponding to such a block, you can, or let's say start it differently. If you start with a Langlands parameter, you have a similar decomposition where you can reduce things to the equivalent of depth 0. And when you do this, you also construct a G0, which is just the centralizer on that side when you restrict to the parameter to the inertia subgroup. Sorry, the wide inertia subgroup. And that is then the dual of this group. So it does match. So I'm not sure, yeah. How does it correspond to the talk to Anne-Marie? So I think this leads on to an interesting discussion, but may I maybe ask to do this after the talk? I'm happy to say more about it. I mean, this whole stuff is also motivated by the L parameter side, but let me maybe defer it to the end. The short answer is it's compatible wherever we know things. All right, any pressing questions? All right. So why is p equals 2 special? So let me start with the definition. Let's say we take V to be an n-dimensional vector space over a finite field. And then I take B a bilinear form to Fp, so bilinear form over this finite vector space. And then I define a group, which I denote by FP and then some funny multiplication sign for the lack of not knowing what else to write. And this is a group that is a group with underlying set just the product of FP and the finite dimensional vector space over FP, but the multiplication is different, and the multiplication, I can't write anymore, multiplication is given as follows. I take two elements, AV and BW, and I multiply them as follows. Well, I could just do it entry-wise, that would be the standard thing. But now I twist this multiplication by my bilinear form. So to the center, I add the output of the bilinear form, B of V comma W. So that just means we have an extension where we have in the center FP, and then we have our group, our funny group. And then as a quotient, we have the vector space. And the multiplication here is given by this bilinear form. And I assume if you want me to switch boards, let me know. I assume you can see everything, but if you want me to switch, okay, maybe I should switch. And I assume that such that the center of this group is just this FP and 0. I mean, FP is obviously in the center. If I put in V and W equals 0, I just add A and B. So then, well, or sorry, if I put in one of them to be 0, then I just add A to it. And so such a group, this funny FP times V, is called a Heisenberg FP group. So we have seen explicitly how it looks like. What is special about this group, and what is special about P equals 2? So here are some facts. So first of all, the zeroth fact is that in order for this center to just be this one copy of FP, we need that n is even. So n should be 2n, should be even. And so once we take an even form, no, I'm not assuming anything right now. Well, I'm about to. If P is not equal to 2, now I assume that P is not equal to 2. Then there exists a unique, I spell it out, a unique, at least up to isomorphism, Heisenberg FP group of any given order. There exists a unique Heisenberg FP group of order P to the, what's the order? It's just P to the 1 plus 2 times capital. So for each order, there's one group. I mean, for each order, we have exactly one group up to isomorphism. And in particular, that means it doesn't depend on the choice of B at all. As long as the center is just the first, just one copy of FP, you can choose whichever B you want. And in particular, we can choose B to be a symplectic form. Let me call this omega a symplectic form. So a non-degenerate symplectic form. Symplectic means non-degenerate. On the other hand, if P is equal to 2, then things are different. Then there exists 2 Heisenberg F2 groups of any given order. At least, well, if the order is large enough, Heisenberg F2 groups of order p to the 1 plus 2n, well, for n greater than 1. Otherwise, it's just fp. So for example, if n is equal to 1, greater, if n is equal to 1, the order is 8. What are the options? There are two possibilities. One is Q8, the quaternion group, or the other is D4, the symmetries of a square, the dihedral group. These are the two options that occur. So we see there's already a small difference. Why do we care about these groups? I want to study p-adic groups. So here's the connection with p-adic groups. So I said, oh, unfortunately, I just erased it. We want to construct this representation via compact induction from compact subgroups. The depth 0 case was the one where we construct representation of finite group of Lie type. But now we want to go deeper down in the filtration, so we need to work with bigger groups. And so here's one example of bigger groups. So let's say G is SL2, G of F is SL2 of QP. Groups we can find inside there is, for example, the group 1 plus PZP, 1 plus, which one did I want to use? P squared. 1 plus P squared ZP on the diagonal, ZP at P times ZP off diagonal. And then I want to quotient out the group 1 plus P cubed ZP on the diagonal and P squared ZP off diagonal. Oops, that's a bit too large. And then always determinant equals 1 inside SL2. And so if we want to construct representation, we have to construct them from compact subgroups that are more complicated. So in particular, one example will be that we construct representation from a representation of this quotient that is trivial on the smaller subgroup. It has positive depth. And if we look at this quotient, I mean, I've written down now to you randomly looking matrices, but it turns out this is actually isomorphic to a Heisenberg FP group for vector space of dimension 2. And I'll leave that as an exercise to work that out if you're bored during the time. So these groups, they appear naturally inside the p-adic groups, and that's why we want to study them. So here's a nice fact. So we want to study this group because they appear in the p-adic groups, but really what we want to do is construct representations thereof. And so what will happen in nature is that we have a character on a large group, which will be slightly larger than that, like the center, and we want to extend it to a bigger group. And so here's the fact, the theory of Heisenberg representation that says for every character from FP that is non-trivial, and so the complex numbers, there exists a unique, and up to isomorphism, irreducible representation, which I call eta sub, phi is how I wanted to call this, rather than psi, eta sub psi, of our Heisenberg FP group, such that if I restrict my representation to the center, so just to this first copy, then this is just the character up here. This is just the character, well, times the identity, because it has higher dimension. So the fact says that if you give me a character on the center, there's a unique irreducible representation of larger dimension that has this character when we, that is isotopic for this character when restricted to the center. And this fact works for p equals 2 the same way it works for p not equals to 2. And so this is what we use in the construction then. But here comes the tricky question. So this would give us a representation of this bigger group, an irreducible representation of this bigger group. But then in practice, what also happens is that we want to extend it even further. We want to extend it also to a group that includes on the diagonal ZP, which acts on this quotient nicely. And so that means what we want to do is, what the question we want to ask is, in general, in this finite group setting, can we extend this Heisenberg representation eta? So that's called the Heisenberg representation. Heisenberg representation. Can we extend the Heisenberg representation eta to a representation of the automorphism group of the Heisenberg FP group? So we want the automorphism group to act on this vector space of the Heisenberg representation in a way compatible with the Heisenberg representation. So in other words, we want a representation of the semi-direct product of the automorphism group with the Heisenberg group itself. And I put a little z here, which means I only consider the automorphisms that fix the center. So fix this FP. And so this is, again, motivated by the construction for p-adic groups where we would like to be able to do that. Yes, oh, yeah. Just mean to extend the representation on the same vector space. So this group here, let me maybe call this, well, I don't want to give. So this group acts on this vector space via eta phi, and we want to have an action on the same vector space by this automorphism group that is compatible with it. So, is that more confusion? So basically, I want to, yeah, that's what I want. I don't want to give it a name because the answer is no. So that's why I'm hesitant to give the representation name, because it just doesn't exist. So, well, that's unfortunate, but it's actually a bit more than what we want. So, but instead, here's what works. So let's work with p not equals to 2 first. So in that case, what is the automorphism group that fixes the center of the Heisenberg FP group? So the automorphism group, let me maybe write this as a short exact sequence. It contains the Heisenberg, it contains the vector space via inner automorphism. So V definitely acts via conjugation, or the whole group acts via conjugation, but the center acts trivially. So it contains V as a subgroup. And then as a quotient, we have the symplectic group for this symplectic form, which is without loss of generality. It's the symplectic form over here. So I choose my B to be as a symplectic, given by a symplectic form. That's the standard way that people usually write Heisenberg groups. And so how does that relate to the automorphism group? Well, it actually, there exists a nice splitting, and I can tell you how the automorphism works. So if you take an element G inside the symplectic group, then G acts on an element AV just by acting on the second coordinate. And since this element G is in the symplectic group, it preserves this form B, and therefore we see that the multiplication here is preserved nicely. So that's how the symplectic group is a nice subgroup of the automorphism group. And a nice fact is that this is all there is. So that's the whole automorphism group that fixes the center. It's just a semi-direct product of the V with the symplectic group. And so here's the nice fact then. And that's what we call Heisenberg-Ray representations, which is that we cannot extend the representation to the full automorphism group, but we can extend it to the symplectic group. So there exists a representation from the semi-direct product of the symplectic group with the Heisenberg FP group. To this space of automorphism of, the complex automorphism of E and sigma that is just on the second copy. It's just the Heisenberg representation. On the first copy, I call it W. Sorry, it's a different one than here. So that is, we call it sub phi. Maybe this is what we call the wave representation. So there exists a nice extension of this representation to the semi-direct product. So we can act with a symplectic group on the space of the Heisenberg representation in a compatible way. And moreover, this is unique in almost all cases. And so the wave representation is unique unless we are in the case that the symplectic group is the group sp2 of F3. Let me not worry about that for this talk. So it's essentially unique. And so this is what people have been using all the time to well, all the time means the last 20 years, more than 20 years, to construct supercustal representations. And the problem now is that this requires really that P is not equal to 2. So let me just say this is used to construct supercustal representation. I'm happy to explain this at the end in more detail if anyone wants to. I just want to show you a bit of where are the troubles, what is making P not equals 2 so different, what are some of the techniques that go into the story. Well, here comes P equals 2. That case is more complicated. We again are interested in the automorphisms that preserve our now F2 Heisenberg group. Well, the center is automatically fixed, but that doesn't really matter. And again, we have the inner automorphisms as a nice subgroup. That's always the case. But now the quotient turns out to be the orthogonal group. The orthogonal group of the following form. So this is the group that preserves the quadratic form, taking a vector and mapping it to B of V comma V. So suddenly the orthogonal group shows up instead of the symplectic group. So the first thing we thought, well, so what? Let's just work with the orthogonal group instead of the symplectic group and we'll figure things out. Well, the abstraction is, unfortunately, there does not exist a splitting in general. So if the dimension of V is greater than 4, there does not exist a splitting. And so that's where really the difficulty comes from, because you saw the theory of Heisenberg representation works the same for P equals 2. But the automorphism group is just a disaster. So what are then the problems? So problems, by problems, I mean problems, abstractions to construct supercuspal representations. Because really, what we did earlier is we extended representation to the symplectic group times the Heisenberg group, and then you realize that inside your p-adic group, the compact group you really care about is really of this shape. It maps to such a semi-direct product. So you construct these Heisenberg wave representation, and then take your big compact group and essentially map it to this, and then induce, roughly speaking. But now we don't have this nice group anymore. Yeah, a problem. So the first problem is there is no nice canonical, well, people who know me know that I don't like the word canonical. There's no nice canonical large subgroup of the automorphism group of the Heisenberg F2 group to which the Heisenberg representation, this eta sub phi, extends. There is just nothing like that because the orthogonal group doesn't split back in. Ring. So how do we, I wouldn't give that talk if I couldn't solve our problems, I guess. So here's the solution to this first problem. That is part of my joint work with David Schween from earlier this year. Well, we just don't work with one group, we just let the group vary. So what we do is, well, there's no canonical group, so we just let the group vary depending on our situation, which means, on the other hand, that we have to prove that always there is a nice group to which things extend. And so that really uses the theory of the p-adic group. So let me put this into words. So we use a large group A that varies depending on the situation. Sorry, I understand this is a bit vague. This is just to give you a rough idea that varies depending on the situation and prove by hand that our representation, our Heisenberg representation, extends. And so this really means that the hard work here is really at the p-adic level. So say using the structure of our p-adic group. So there's really the things that happen now is that we need to work hard at the level of the p-adic group to show there exists a nice subgroup that works and does the things it should. And in particular, for those who know a bit this story, so the person who constructed a lot of representations, I'll recall this in a moment, JKU, used these Heisenberg wave representation and then used the result of Jordan about the structure of these Heisenberg wave representations. In particular, he used the structure theory of what happens when I restrict my Heisenberg wave representation to a parabolic subgroup here. Then I get a new Heisenberg wave representation, unfortunately twisted by a character, which led to a lot of drama. That's another fun story for some other time. And so we don't have that anymore. We don't have the whole theory of Jordan where he understands these wave representations very well. So that means we have to work these things out by hand. But instead, it also means that we avoid things that have caused problems in the past. P is 2, yeah, sorry. No, it's disconnected. No, it's yeah. So let me just say this once more into the microphone. This is really the disconnected group. It's defined via the Dixon variant, things like that. So it is disconnected. the one that preserves this quadratic form here. Yeah. I mean, there is a B, but there's no symplectic form in the for p equals 2. I mean, B is a bilinear form that is not symplectic. No, but that's a. Yeah, I'm happy to put a B in the notation. That clarifies things. I put it. Which actually makes things much more complicated, the fact that it's not disconnected, that it's not connected. That was problem 1. Problem 2 is, okay, now we have, sorry, any comments, questions? Problem 2 is now we have an extension, but there might be many extensions. So problem 2 is that in general, so if omega eta is an extension of eta, then so is any twist by some character. For some character psi from our group 8, which we extend to the complex numbers. So that means, in general, this extension is not unique. And so how on earth do we choose something? So in this case of SP, it was unique because SP doesn't have any characters unless we work with SP2 of F3, where you can choose one. And so here's the solution. Which is, there's a really nice feature that only happens, well, it's really an if and only if P is equal to 2, then the Heisenberg representation is self-dual. And so our solution is that we require the extension, the Heisenberg ray representation, to be self-dual as well. Well, and we prove that exists, such a representation exists, and prove existence. Which then means, so this means then that this representation omega W is unique up to self-dual character, which means just a map from A to really plus minus 1. And in our applications, there are no self-dual characters. So in our application, it is unique. Oh. So let me just add this in parentheses. In our, oh, I'm not allowed to use parentheses, I was told. Unique in our application. All right, so that's hopefully giving you an idea of why is P equals to so different from P not equals to 2. Because of the theory of Heisenberg ray representation that underlies a lot of the constructions, and that we had to come up with all kinds of other things to resolve that, which took somehow more than 20 years. And I want to finish my talk by now actually putting everything back together and drawing the picture of what we know about the representations of p-adic groups now. So, well, let me remove the sentence again to have a bit more space. So it's unique in our application. So construction of supercuspidal representations. So what do we know about the construction? Let me say, we know that all supercuspidal representations have been constructed in the case of GLN. That was known for a long time now, 30 years. It started more than 50 years ago by work of Howe and Moy and was finished by Bushnell and Kutzke. We also know inner forms of GLN thanks to Seychelles and Stevens 15 years ago. And we know classical groups thanks to work of Sean Stevens in the case that P is not equal to 2. So we assume P is not equal to 2 even for classical groups, so for fixed points of an involution, so for orthogonal, symplectic, and unitary groups. All these rely on the use of GLN. And so I want to draw the picture now for general G. And so for general G, it started with work of Moy and Bressett in the 90s. They defined the step 0 representation that I told you about at the beginning. And so I want to draw a picture where I draw the depth in that direction. So that's the depth. The depth can be 0, or it can be a positive real number. And so Moy and Bressett, they then defined and studied the depth 0 representations, where in this direction, I want to draw the prime number P. And so everything that has depth 0 here, that was what Moy and Bressett did in the 90s, 94, 96. And that's what I started my talk with. And that's what we reduce a lot of questions back to now. And I should also add in Morris, who worked on this and did something similar in 99 using Hacker algebras. And then people tried to construct positive depth representations. So Jeff Adler constructed some representations. So that was Jeff Adler in 98. And then JKU generalized this construction vastly. And I guess I put my own initial there for showing that the construction actually works. And so there are a lot of representations which I now draw as circles here of positive depth and depth 0 that they constructed. And that uses the construction of the Heisenberg-Weyl representation. And that's why they assume that P is not equal to 2. So if I draw the 2 here, say 3 here, then we see in the region of 2, there's just nothing. Nothing could be constructed for P equals 2 because of the need of the Heisenberg-Weyl representation. And then the question is, how much do we get out of that? And so then in 2007, Julie Kim had a big breakthrough when she showed that the prime P is very, 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 very large. Then we get all the supercuspidal representation under the assumption that the characteristic of the field is equal to 0. Then Julie Kim proved in 2007 that everything arises from use construction. So I didn't tell you just about the construction of some representation. Actually, this is the construction of all representation under that assumption. And then I've proven in 2021 that if we only assume that we are in the region where P is large, by which I mean P doesn't divide the order of the Weyl group, in this region, we also get everything, and we don't need to make any assumption on the characteristic. That was 2021. So that means if P is large, we have everything. And that is what I was asked at the beginning, that I said somehow we know almost everything. And that's what I mean with almost all. So if P doesn't divide the order of the Weyl group, then we can construct everything. But there was nothing here for P equals 2. And so that's now the work that I've alluded to throughout the talk. I joined work with David Treen, in which we now managed to finally extend use construction from more than 20 years ago to also work for P equals 2 by circumventing the use of the Heisenberg-Weyl representation. And actually, we did slightly more. We also added some more representations for small primes P by removing some not needed genericity condition that I glanced over. So that's really now the picture. And if anyone is interested, I'm happy to afterwards tell you a bit more how we use these Heisenberg-Weyl representation to construct representation of p-adic groups. But I think for the general audience, I stop here with the nice picture. Thank you.